Hi everyone, these are notes for Objective 4 on Unit 13, and we're stepping away from doing the slope formula for finding the slope of a tangent line, and we're going to instead be working with approximating area between a curve and the x-axis on a defined interval. And we're going to be doing that using rectangles. And for now, we'll be using rectangles that are equally spaced or of equal width. And later on, we'll use rectangles of varying sizes. So the first thing we're going to do is we're going to walk through the different kinds of rectangles we're likely to run into: inscribed, circumscribed, and midpoint rectangles. And we're just going to draw out what each of those cases would look like. So starting with inscribed rectangles, you can read here, it says the height for each rectangle or each subinterval is found where the lowest height for each rectangle touches the curve. So the lowest side could be the left, it could be the right, as well as somewhere else within the interval, as the height for each rectangle might change. No part of any inscribed rectangle can go above the curve. Approximations with a finite number of inscribed rectangles is always an under approximation of the actual area. So we are going to take our interval AB here for the first f of x, and you can see we've got some markings down here at the bottom. We're going to label these x sub 1, x sub 2, x sub 3, and x sub 4. And so those are our divisions from a to x1, from x1 to x2. These are the equally spaced rectangles here at the bottom. Those are the widths. So the height of each rectangle has to be chosen from the lowest point of the interval. So notice if I march A up to my curve versus marching x1 up to my curve, this curve has its lowest point when x is a. That's the lowest point of that interval, since the curve is increasing as it goes to the right. So this point here that I've marked on my curve will be the height of the first rectangle, whose width is from a to x sub 1. So that's the first rectangle. Okay, the second rectangle from x1 to x2. So if you start to see what's happening here, you can see that above my curve is still increasing on this interval. So the lowest point right now is still over here on the left. So when the x value is x sub 1. So this point right here, that will give me the height for my second rectangle. Okay, from x2 to x3, so it increases a little bit, and then to get to x3, it actually comes back down a little bit more. So the highest point, or the lowest point in here, the lowest point appears as though it might be x3, but it could also be x2. Those almost look like the same height. So we want to just choose whichever one appears to be lower. So I'll use x3. But maybe they are actually at the same height, so either one could be used. From x3 to x4, the curve is now decreasing only, so the lowest point on the curve is over on the right side at x4, so the right side of the rectangle, the right side of the fourth rectangle. Okay, so from x3 to x4, x4 gives the lowest point on that interval. That then is the height of this rectangle. And then as it comes down to the b value, we're still decreasing, so that's the lowest point here as well. So you can see that sometimes the height came from the left side, sometimes the height came from the right side, or sometimes it could have come from either side. If we could have a better idea of where it came from, we would know. But just using a picture, that's the best we can do for now. So those are your inscribed rectangles, and you can see the little bits of area that it leaves out right? We want to approximate area between the curve and the x-axis. So there's all these little pieces in here that get left out. That would give me the actual area under the curve. So hopefully you can tell then that this is an under approximation. So let's go on to circumscribed rectangles. So the height for each rectangle here is found at the tallest height for each rectangle, choosing the higher side, which might be the left or the right side, or even somewhere in between as the height of each rectangle changes. A little bit of each rectangle should go above the curve. Approximations with a finite number of circumscribed rectangles is always an over approximation of the actual area. So let's get into drawing these rectangles here. So we're going to label them like we did last time, x1, x2, x3, x4 on the interval AB. So from A to x1, as the curve is increasing left to right, the highest point here is at x1. And so that will actually be the height of the first rectangle at that point. This is the height. So you can see it's circumscribed. We have a little bit of each rectangle will go above the curve. There's actually, it looks like quite a bit of the rectangle that goes above the curve, and that's fine. So from x1 to x2, the graph is still increasing. So the highest point again is at x2 on the right. That will give me the height of the rectangle. So there's just a little bit above the curve. From x2 to x3, I think we judged those points to be about the same, or maybe x2 is just a tiny bit higher. So we've got just a little bit of area above the curve there. From x3 to x4, the highest point is at x3. So it's switched. For this rectangle, the highest point is on the left, and that happened because my curve changed. It was increasing, and now it's decreasing. So the side that we use changes. Same thing from x4 to b. The highest point on this curve is at x4. So that will be the height of this last rectangle. And then again, you can see all the little bits that were above the curve that averaged too much. So if you're thinking those might be equal to the amount we were under approximating from the first example, it's close, but they're not equivalent. So although I could average these two things, their average would give me an even better, closer approximation to the actual area, but it still doesn't calculate the actual area. So there's one last thing we can do that's a really good measure for approximating area. Besides using inscribed and circumscribed rectangles, is using midpoint rectangles, in which case the height for each rectangle is found at the midpoint of each subinterval. So it's not necessarily the highest point or the lowest point, it's just strictly the middle of the interval. When using the same number of finite rectangles to approximate the actual area under the curve, but above the x-axis, midpoint rectangles will always be the most accurate. So this is even faster than doing inscribed or circumscribed and averaging them. So let's take a look at drawing our rectangles in here. So from A to x1, we pick the point that is right in the middle. So at that x value, if I take that x value up to my curve, make a point, that is the height of the rectangle from A to x1. Okay, and so you can see there's a little bit of area that ends up above the curve and a little bit of area that gets missed under the curve. Okay, and that's that first rectangle there. So from x1 to x2, again, we pick the x value right in the middle. We take that as our x value up to our curve to plot a point. That's the height for the rectangle from x1 over to x2. Again, you can see a little bit that gets missed under the curve and a little bit over the curve. So we'll repeat this halfway between x2 and x3 up to our curve. Okay, that's our height there. Halfway in between x3 and x4 takes us up to a point on the curve. That's the height for the fourth rectangle. And then the last one, halfway between x4 and b, we'll take that up. And then that's the height there for the last rectangle. So you can see it didn't matter which end was lower or higher. I didn't use any information like that to judge where it should be. All I did was pick the height that's obtained from the x value in the middle of the interval. All right, so that gave me each rectangle. So again, remember that those midpoint rectangles are going to give you the best approximation. So averaging inscribed and circumscribed will give you a really close estimate, but this one will be just a little bit closer. All right, so we're going to move down in the notes here to the examples below and approximate the area under the function given, f of x. You can see it's just a nice parabola here. And so we've got 3 cases, so it is drawn 3 times. Feel free to draw your shape as many times as you need for your different rectangle sizes. If you feel you only need to draw it once, and you can just use one picture to do your different rectangles, that's fine. You just want to make sure that all of your different approximations are labeled clearly. So when you do your inscribed, make sure you label it that way, circumscribed, label it, and midpoint. So let's start with, it says part A, 3 inscribed rectangles with equal subintervals. So notice our interval here. It says we're using the interval -1, 5. So I'm going to mark -1 to 5. Okay, now that is a width of 6 units from -1 to 5. So it's just 5 minus -1, a width of 6. And then we're supposed to split them equally. 3 rectangles equally spaced. So I take my total width and divide it by the number of rectangles, and it tells me the width of each rectangle will be 2 units. So the first rectangle is -1 to 1, then 1 to 3, and then 3 to 5. So they're each 2 units wide. To do inscribed rectangles, we're going to draw them in first. We want to choose the lowest point on the curve. Notice from -1 to 1, my curve is only decreasing on that interval. So the lowest point occurs at +1, and that'll be the height of the first rectangle. We can do the same from 1 to 3. The lowest height from 1 to 3, the curve is still decreasing. The lowest point is at 3. That'll be the height of the second rectangle. You might notice that it could potentially happen where the lowest point actually touches the x-axis. That's okay if that does happen. Say this vertex came down and touched the x-axis here, then the height of your rectangle would be 0, and the area of that one rectangle would be 0, and that's fine for an under approximation. Okay. From 3 to 5, the curve is now increasing, and the lowest point now occurs when x is 3 again. So the height of the last rectangle is the same as the second one. So that's what this looks like. So we're going to set it up over here on the side. We are approximating area, so I'm going to use my congruency symbols. And then what we're going to do is, remember the area of every rectangle is width times height. So I have the first rectangle has a width of 2, and then the height, right? How would we find that height? How would we know what that y value is, the height of that rectangle? Well, we get that height from plugging in the number 1, right? If I plug 1 into my function here, it would tell me the height of that rectangle. So I'm simply going to write f of 1. Okay. The next rectangle has a width of 2. And then how would we find the height? From plugging 3 into the function. That gave me that point on the graph, so f of 3. And then the last rectangle has a width of 2, and then the height is found again from plugging in 3. All right, so whenever we have equally spaced rectangles, we have what's known as the common width of 2. So to make the math go a little bit faster, what we'll start doing is factoring out the common width, which will leave inside f of 1 plus f of 3 plus f of 3. And that is the height of each rectangle. So 1, 2, 3 heights for 3 rectangles. Okay, so I've left them inside. And now we'll go ahead and evaluate. So f of 1 is 5. F of 3 is 1. Okay, so this comes out to 14. And again, that is an under approximation. All right, so part B says to use 3 circumscribed rectangles of equal subintervals. So we're going to do the same thing. Our width is going to be the same. It's an interval width of 6 units from -1 all the way over to 5. And then we're dividing it by 3 rectangles. So each one still has 2 units of width. Okay, so -1 to 1, 1 to 3, and 3 to 5. So let's go ahead and draw our rectangles, circumscribed. Choose the highest point along the curve. From -1 to 1, the highest point is going to be at -1, since the curve is decreasing as we go, right? So we want to choose this point at -1, and that will be the height for my first rectangle. So quite a bit of area there over the curve that we don't need. From 1 to 3, the curve is still decreasing, so the highest point occurs at 1. So this point here will give me the height of the second rectangle. And for the last one, the curve is now increasing, the highest point being over here when x is 5. So this will be the height of my last rectangle. So let's find that area now. So I have, we're just finding the area of each rectangle and then adding them together. So the area of the first rectangle is 2 units of width. And then my height, so what number did we plug into our function to get the height of that first rectangle? We plugged in -1, f of -1. The second rectangle has a width of 2. To get the height here, we plugged in 1. So now we're going to plug 1 in to the function. And then for the last rectangle, again, a width of 2. And to get the height, we had to plug in 5. So again, we want to practice factoring out that common width since they're equally spaced, which will leave only the sum of the heights. So f of -1 plus f of 1 plus f of 5, so the sum of the heights. And then we'll do our substitutions here. So f of -1 is 17, f of 1 is 5, and f of 5 is 5. So this comes out to 54, which is quite an over approximation. And those are very different answers. I've got 14 versus 54, right? If I were to average those numbers, since we talked about averaging them, and I'm sure every once in a while you'll have directions to average those values and see what answer you come up with. So the average of these values comes out to 34. So that's at least a better idea of what the area might be, but it's not the best. Remember, the best approximation comes from midpoint rectangles. So in part C, we're going to do midpoint rectangles, 3 of them, equally spaced. So from -1 to 1, from 1 to 3, and from 3 to 5. So in doing a midpoint rectangle, you're going to purposefully choose the middle of each interval. So the middle of -1 and 1 as 0, we take that up to our function here to plot a point, and that is the height of the first rectangle from -1 to 1. So maybe I'll write down my area as I go. So I have a rectangle of width 2, and the height is taken by plugging 0 into the function. The second one, we have, again, a width of 2, and then to get the height, the middle of 1 and 3 is 2. So by plugging 2 into my function, it gets me to this point here, and that will be the height of this rectangle. So f of 2. Okay, the third rectangle has a width of 2, and the height is from the middle of 3 and 5, which is 4. By plugging 4 into the function, we get this point here, and that will give us the height of the third rectangle. So 2 times f of 4. So each time I did write it out the long way, width times height, and then I've been factoring out the common width. But you can just jump to that step in the future and start here, just with your common width already factored out, and that'll make your work just a little bit faster. So we make our substitutions. F of 0 is 10, f of 2 is 2, and f of 4 is 2. And this comes up to 28. So 34 for the average versus 28 for midpoint. This is our best approximation. But it's still not the actual area under the curve, which is fine. And that's all we need to know for now. On the homework assignment, you'll be practicing with inscribed, circumscribed, and midpoint rectangles. On your intervals, they're equally spaced, so equal widths. Sometimes the number of rectangles will change, so watch out for that as well.